Hello everyone, and thanks for watching Edupedia World videos. So continuing with the topic of liquefaction. Okay, so in this session we'll finish up this process. Okay, so last time we were looking at this graph, alright, and we saw that finally at a temperature of 30.98 degrees centigrade the carbon dioxide gas, okay, was able to get liquefied, but for that temperature value we needed a very high pressure value. Specifically we needed a pressure value of 73 atm, okay, or bar to be more precise, in order to liquefy the gas. And we also concluded that if I am able to decrease my temperature below this value of 30.98 degrees centigrade, I can liquefy carbon dioxide for pressure values even below 73 bar. Okay, so that is I can liquefy the gas even for lower pressure values, relatively lower. The pressure will still have to be high, but not very high. So let's look at that. What happens if temperature is lower than 30.98 degrees centigrade? Let's come to the fourth line, the line which is purple colored. Okay, so this line where points A, B, C, D. Okay, so this is the isotherm which we are talking about now. So in this isotherm, once again we are starting from the right hand side where carbon dioxide is in gaseous form. Okay, so here it behaves completely like a gas. That means even for slight changes of pressure there is significant change in volume. Okay, so that is the gas is going to be, okay, quite compressible. So this continues to happen up to point B. Alright, that is your CO2 is acting just like a gas which you expect. Alright, but once it reaches point B, it has come into the contact, okay, it has come into contact with the dome shaped structure that we have here once again. Okay, so now our gas is in contact with this dome shaped structure. So what happens is here at point B, okay, here at point B something changes. Alright, from A to B the gas or the CO2 was completely in gaseous form, but as soon as point B is reached, this is the point where we see the first droplet of liquid CO2. Okay, so if this is my container which initially had only gaseous carbon dioxide, alright, so it only has gaseous molecules here. At point B I finally get a droplet of liquid, okay, a droplet of liquid CO2. So the gas is still present, but there is also liquid with it. Okay, so this is the moment where the equilibrium starts. Okay, this is the moment where our liquid and vapor are going to be in equilibrium. Okay, so here we know that vapor was present and now I will have liquid also. Okay, so now I am writing vapor over here instead of gas because now this gas has the capacity to get converted into liquid. So after this point B, that is once the equilibrium has started, okay, this physical process, okay, has set in. After this, not only your temperature is constant but pressure also becomes constant. Alright, so once B point was reached, the isotherm entered the dome structure, and inside this dome pressure doesn't change for a given isotherm. Okay, so this is what happened, that temperature and pressure are now both constant, but the volume is still decreasing. So how is that happening? That is happening because more and more gas, as we move from point B towards point C, okay, more and more gas is getting converted into liquid form. That means the volume of gas is obviously decreasing. So initially only one droplet was there, now there will be more droplets of liquid CO2 coming in. So why is not there a change in pressure? Well, let's assume there is a change in pressure. After point B, I still want to increase the pressure, so I can do that externally, right? So what I'm going to do is I'm going to increase the pressure while maintaining the temperature after point B. Okay, so what system will do, okay, in retaliation to that external increase in pressure is it will convert more gas into liquid form. Okay, since I'm increasing the pressure, the gaseous molecules will come close to each other. Okay, and now it already has a tendency to form liquid. It has already formed the first droplet at point B. Now since I'm increasing the pressure, that tendency further increases and the gas gets converted into liquid. So more and more gas gets converted into liquid as you keep on increasing the pressure after point B. Alright, so what system does is, in retaliation, it converts itself into liquid form, but it doesn't allow to change its own pressure. Okay, so you have increased the pressure, the system will convert itself into liquid form, and since gaseous molecules have now decreased as they got converted to liquid, the pressure automatically decreases back to the initial value which was at point B. Okay, so this is what happens up to point C. Even if you keep on trying to increase the pressure, more and more gas gets converted to liquid, more liquid, and at point C finally you get, okay, at point C you get the last droplet of liquid. That is, at point C every molecule of gas has now converted to liquid carbon dioxide. So now if you try to increase the pressure after C, okay, so now there is no more gas left. That means now the system can't retaliate, okay, the increase in pressure by converting gas to liquid. Now everything is in liquid form, so it has no other option than to decrease its volume with increase in pressure after point C. But since we have liquid here now, there is no more equilibrium. From B to C the equilibrium existed, but now the equilibrium is gone since the vapor is all gone. So after point C, a liquid is being compressed by increase in pressure, and we know that liquid are not so easily compressible. So that is why now the change in volume, even with very high increases in pressure, is not going to be so much. Alright, and that is why the slope of the curve, though still negative, is very steep. Okay, the curve is very steep. That is, the value of slope or the magnitude of the slope is very high with a negative sign. Okay, so after point C, now liquid will forever remain as long as we keep pressure greater than the pressure at point B, okay, which is this pressure value. Okay, and this is, okay, this is the nature of every curve below temperature of 30.98. so whenever temperature is less than this value, the tendency to liquefy is high and the nature of the isotherms is similar. Okay, the only change is in the extent of the horizontal portion, okay, or the threshold pressure at which the liquefaction starts, that is the first droplet and the last droplets are formed. Okay, that changes for each isotherm, but the overall nature, okay, is same. And as you keep on decreasing pressure, this threshold, sorry, as you keep on decreasing temperatures, the threshold pressure will obviously keep on decreasing, and the amount of time, you can say, okay, not exactly time, alright, but the length of the horizontal portion keeps on increasing. Okay, okay, so the length, you can say, indicates the amount of time spent in the equilibrium phase. Okay, so let's talk about equilibrium phase a bit more. Alright, how is this different from gaseous phase and the liquid phase? Okay, and how is it different from point E, where I did not tell you that there was an equilibrium? The equilibrium comes into picture only once you enter the dome, okay, not when the isotherm is just tangent to the dome. So in this equilibrium phase, there is gas and liquid in the same container. That is, there is a distinct difference between the gaseous molecules and the liquid molecules of carbon dioxide, and this distinct difference can be seen, okay, in form of a surface, okay, the topmost layer of liquid, okay, which forms the surface separating liquid from gas. Alright, so at this surface the exchange of molecules takes place. That is, the liquid can get converted to gas and the gas can get converted to liquid at this topmost layer. Below it everything is liquid, above it everything is gas. Alright, and this distinct existence of phases, okay, phases, is only when we are inside the dome and only when there is an existence of equilibrium. Alright, at point E there was no such equilibrium, and hence there was no such distinct phases between gas and liquid. So in the same container at point E we did not have gas and liquid present at the same time. Okay, so we'll look at what this means in the subsequent slides. Alright, so this basically finishes up the liquefaction process. Okay, you should now be able to understand this process completely. Okay, and now we'll finally move on to some definitions and technical terms which you just have to memorize over here. Okay, the first of them is the critical point. Okay, so what does critical point mean? So the critical point is the point E. Alright, it is the point at which liquid and gas cannot be differentiated. Okay, the point E in our graph was the critical point. Okay, there I cannot say whether my substance is in liquid phase or in gas phase because there is no way to differentiate between liquid and gas phase. Okay, usually how do we differentiate between liquid and gas? We can measure their densities. Alright, density of liquid phase, density of gaseous phase, or we can manually, okay, observe that there is a distinct surface separating the two phases, or I can calculate some other physical property like refractive index. Alright, or I can calculate, say, coefficient of thermal expansion. Alright, or any such physical property of liquid phase and gaseous phase, and they will have different magnitudes, different values. But at point E, okay, at point E of our graph, which was called the critical point, this distinctions doesn't exist. The value of physical properties, whether it is density, refractive index, or any other physical property which you can think of, the value of these physical properties are same both for liquid phase as well as gaseous phase, and hence there is no way to say whether at point E I have gas or whether I have a liquid. What I can say is that on the right hand side of point E I have gas, and on the left hand side of point E I always have liquid, but I don't know about the point E itself. Okay, so that is what we mean by critical point. Alright, physical properties in two phases have the same value. So this point E mathematically is also the point of inflection. Alright, so we won't go into detail of what that means, okay, but we will look at some other terms over here. Alright, so this point E, okay, it lies only on a specific isotherm for a specific real gas. So for CO2, point E was point lying on the isotherm which had temperature value of 30.98 degrees centigrade. Alright, so point E can only be attained, or we can observe point E or reach point E only if I am traveling on this isotherm of 30.98 degrees centigrade. Okay, if I am at any other temperature values, I cannot attain or I cannot reach point E. Okay, I will either be above the dome or I will either be inside the dome, but not just tangent, okay, but not at a tangential position to the dome. Alright, and this temperature value can have different value for different gases, and hence it is a characteristic of a gas. So even the critical point is a characteristic property of a given real gas. So it will have different positions, different coordinates for different gases. Like if you compare nitrogen and CO2, or say ammonia and methane, they will all have different critical points. Alright, and different temperature values using which we can reach that critical point. Okay. So let's talk about this temperature value now. This particular temperature which helps us to reach the critical point is called critical temperature. Okay, it is represented by Tc, and it is, in definition terms, okay, in verbal terms, it is the maximum temperature up to which a gas can be liquefied. Okay, because if you remember the curve, okay, this is how our curve looked like somewhat, and if you remember this curve, we said that above this temperature, alright, this is my Tc curve. Okay, that is my critical temperature isotherm. Above this curve, that is, if temperature is greater than Tc, that is, it is greater than 30.98 degrees centigrade, then my gas cannot be liquefied. Okay, no matter how high the pressure I am applying. that is Tc is the maximum temperature up to which liquefaction process is possible. Above that I will always have only gaseous phase, and below that I can have either liquid or gas or both in equilibrium with one another. Alright, so this isotherm which is tangent to the dome shaped structure is called critical temperature. Alright, so you have to remember this definition. It is the maximum temperature up to which a gas can be liquefied, or you can say it is the minimum temperature up to which a gas cannot be liquefied. Okay, we are talking about a real gas obviously, because ideal gas don't undergo in liquefaction process, so it is meaningless to talk about them. Alright, now even at critical temperature I needed a particular value of pressure for liquid to actually form, right? Even at Tc, on the right hand side part of the Tc isotherm, everything was in gaseous phase. Okay, here CO2 is in gaseous phase. Alright, at E I don't know what it is, but after E I know it is always in liquid form. So this at this point E, at point E there was some particular value of pressure which was 73 for CO2 that I needed to apply in order to convert my gas to liquid. So this pressure is called critical pressure. It is the minimum pressure which must be applied at critical temperature to liquefy the gas. Okay, minimum pressure. So if you keep the pressure value above this, the gas will be in liquid form. But if you keep the pressure value below this, the gas will always be in gaseous form. It will not get converted to liquid form if pressure is below this critical pressure on your critical temperature isotherm. Okay, so this is represented by Pc. Okay, so do remember that Pc is defined only for a particular temperature, that is the critical temperature. Okay, and for CO2 the value of critical pressure was 73 bar. Okay, so this point E will be my critical point, and the value of temperature at critical point is called critical temperature, and the value of pressure at critical point is called critical pressure. Okay, so you can also define critical pressure as the maximum pressure at critical temperature for which gas cannot be liquefied. Okay, it is the maximum pressure for which liquefaction doesn't take place. If you are above it, liquefaction will always take place. Okay, and the gas will get converted into liquid form. Alright, as long as we are at Tc. Okay, next we should know what critical volume means. So it is very simple. We already know what critical pressure is, and we already know what critical temperature is. So critical volume is simply the value of the volume, okay, or the volume of gas, okay, specifically 1 mole of gas at Tc and Pc. So you have fixed the amount of gas, that is 1 mole, you have fixed the pressure value, that is Pc, and you have fixed the temperature value, that is Tc. So automatically the volume value will get fixed and you cannot change it. Okay, it is out of your hand, and this volume value is called critical volume. It is the volume occupied by 1 mole of gas at critical temperature and pressure. It is represented by Vc. Okay, capital V with a subscript of C. Alright, so again at critical point, that is point E, the value of temperature was called critical temperature, the value of pressure was called critical pressure. Okay, and the value of volume for 1 mole of real gas, if I had 1 mole of CO2, then the volume of that CO2 will be called critical volume. Okay, and experimentally it is very difficult to actually calculate this volume. Alright, so it won't be same as volume of container. It will have a unique value for CO2. Alright, for a given real gas, Vc, critical volume, will have a unique value. It will depend on intermolecular forces and the size of individual molecules, so we cannot actually calculate Vc. Okay, but you can calculate the values of all these 3 critical variables, that is critical pressure, temperature and critical volume. You can calculate values of this using van der Waals constants A and B. Alright, so you don't have to do that as per your NCERT or CBSE syllabus, but for JEE purposes the formulas of TC, PC and VC are important in terms of A and B. Okay, you have to remember those formula. When you look at those formula, you will see that critical volume depends on the value of B, whereas critical temperature and pressure depends both on A as well as B. Alright, and that is why we can say that this critical point, okay, this critical point and the variables at critical point are characteristic of a gas, because their values depend on A and B, which are called van der Waals constant and which are characteristic property of a given real gas. Okay, so let's analyze this liquefaction process a bit further. Okay, slightly, just one last thing. So the question is which often students ask is that, is it possible for me to convert a gaseous substance, okay, into liquid substance without going through the dome shaped structure? Alright, everything that we studied was happening because of this dome shaped structure, where equilibrium existed between gas and liquid, and where in the same container both gas and liquid phase were distinctly present. Okay, and the critical point was, okay, the point which was tangent to this dome. Alright, and that was the temperature, okay, maximum temperature up to which liquefaction can take place. So is it possible for me to not go to this dome and still be able to convert, okay, still be able to convert my gaseous substance to liquid substance? The answer is yes, you can do that. Let's see how can we do that. Okay, let's look at the curve again. Okay, so we'll have to be smart about it. Let's assume our gas is, okay, our gas CO2 is somewhere, let's say at some random point, let's call it A. Okay, the gas is at point A. My goal is to convert this gaseous CO2 completely into liquid CO2, but without going through this dome shaped structure. Okay, I do not want to touch it, I do not want to go through it. So how do I do that? Well, what we can do is we can increase the temperature. Okay, the first step that we are going to do over here is we are going to increase the temperature so that my gas is now at point F. Alright, so while maintaining the same volume, I have increased the temperature. That is, now I have shifted to an entirely different isotherm, the green colored isotherm. Now at point F, I know that I am at green colored isotherm, which is beyond the dome structure. That is, it is an isotherm which is above the TC value, and hence, okay, hence on this isotherm my gas will always remain in gaseous form and it will not get liquefied. So let's keep on increasing the pressure, keep on increasing the pressure, keep on increasing the pressure, which will result in decrease in volume up to point G. Alright, once you reach point G, stop increasing the pressure further. Okay, so now I know that I am at point G, where the volume value is V1, okay, and the pressure value is a very high value. Okay, and here CO2 is present completely in gaseous form and not in liquid form. Now let's again shift to a different isotherm. Okay, so how can I do that? I want to convert this gas to liquid. So to convert from gas to liquid, I should decrease the temperature, right? So let's shift to a lower isotherm, an isotherm which has lower value of temperature. So let's shift to the critical isotherm. Okay, that is, we have shifted from point G to point H by decreasing the temperature of my gas while keeping the volume constant. Alright, so from G to H, now I am at point H. Alright, and what do I know about point H? Point H represents the critical temperature isotherm. It is the first time, it is the isotherm for which the first time gaseous CO2 gets converted to liquid form. That means, okay, I am at that isotherm where liquefaction is possible, and moreover I am at a point on that isotherm which is beyond E, okay, which is on the left hand side of E. That is, I am already in liquid phase. So just by decreasing the temperature, I shifted from point G to point H, okay, and as soon as I reached point H, I got liquid CO2. All of my gaseous CO2 got converted to liquid CO2 without going through the dome shaped structure. That means liquefaction took place here without going through the equilibrium process. Alright, so this is how you can do that. Okay, so even at point E there is no equilibrium existing between gas and liquid, and by following this method which I just showed you, that is by going through an isotherm above TC, also I can make liquefaction happen without establishing the equilibrium between gas and liquid. Alright, so just remember this point. Okay, so you won't get a direct numerical questions, okay, in your school exams based on this, but you can get qualitative questions. Alright, and in JEE you can also get numerical questions based on the formulas of the critical pressure, temperature and volumes. Okay, so you can focus on all of that, and this basically finishes up your gaseous state. Okay, in the next session we'll start with liquid state, though we are still studying the chapter of states of matter. Okay, and there is another thing that we have to study, which are different kinds of intermolecular forces in gaseous molecules, or whether it might even be in liquid molecules. So we'll look at that towards the end of the chapter. Okay, so until next time, and once again thanks for watching Edupedia World videos.